Let's take a look at an application of natural logs and logs in general. One of the applications of a natural log or of using E is in finance. We have something called continuously compounded interest. This is interest that it continuously gets added to the principal when you put it into an account. And we have an equation that can help us calculate how much money is in there at any given time if we know a certain parameters. So here's our equation. We have A, which is the amount in the account at the end or whatever time period you're looking at, equals P, which is the principal or the original amount that you invested into that account, times E. Remember, E is not a variable, it's a constant, to the rate times time. Rate is always given in decimal form. So R is always as a decimal. That means if it's given to you as a percent, you need to move it 2 places to the left. And T is always given to us in time and years. So when Angela was born, her grandparents deposited $3,000 into a savings account and it paid 4% interest compounded continuously. Assuming that there are not deposits or withdrawals from the account, what will be the balance after 10 years? And we're going to use this formula. So I'm going to write the variables from this formula over to the side, and that will help me decide what goes where and what I need to solve for. So when Angela was born, her grandparents deposited $3,000 in her account. So that's how much they started with. That means that's their principal. And the account paid 4% interest rate. 4% as a decimal is 0.04. And it's compounded continuously, which told us to use this equation. Assuming that there are not deposits or withdrawals from the account, what will the balance be after 10 years? That's time. That means that I'm looking for the amount of the account balance. So let's plug what we know into the equation. A equals 3,000 times E to the 0.04 times 10. Well, lucky for us, the variable that we're trying to solve for is already by itself. All I need to do is type into my calculator 3,000 second e to the 0.04 times 10. Now, if your calculator does not give you the exponent actually in the exponent location, make sure that you put your exponent in parentheses. A is equal to $4,475.47. Whenever you're trying to find money, you always round it to dollars and cents, which is 2 decimal places. Let's do another one. How long would it take the account to reach at least $10,000? So A, P, R, T. And this time it says that the account is going to reach at least $10,000. Doesn't change the fact that they put 3,000 in the beginning and that it's growing at 0.04 for my rate. So that means we're looking for time, and it asked how long, so time makes sense. So I have 10,000 equals my principal times e to the 0.04, and I'm looking for time. Now, this is why it's in this chapter. I have a variable as an exponent. So just like we practice solving in the problems at the top of the page, we need to get this power all by itself. We do that by dividing by 3,000 on both sides. It's going to be a decimal, but we can use it as a fraction. 10,000 divided by 3,000. Change it back to a fraction. Anything that can be changed to a fraction should be. And we deal a lot in this chapter with numbers that can't be, especially in those last 2 skills and the last standard. But this one can be. So we will and we've been given e to the 0.04t on the right side. So this power is all by itself. That means it's time for us to change it into logarithm form. Now this time the e is on the other side, so your loop is going to go counterclockwise if you're drawing with the loop. Otherwise, you can know that I have log base e, which is natural log, or ln, of 10 thirds is the number I was trying to get to. And 0.04t is the exponent I used. So let's find out, what is the natural log of 10 thirds? ln 10 thirds. It is 1.20, and that 39 changes to a 4 because of the 7. Now I need to divide both sides by 0.04. And I get t is equal to 30.099 years, or 30 years. Time and years we can usually round to a whole number. Another application would be in population growth or population decay. We still have continuous compounding growth here. So a current census shows the population of a city as 3.5 million. This is our formula that we're going to use. Find the expected population of the city in 30 years. If the population growth is R, 1.5, which is what we're used to, R being the percent of growth. But this time it says that A is our current population. This is different than what we just saw in our finance problem, where it had A is the final account balance. This time A is my starting number, and P is going to be what we're looking for, or what our population is at any given time. So this time I have P and A, R, and T. So they've given us the current population, 3.5 million. The growth is 1.5%, which as a decimal is 0.015. And then they said 30 years. So this is what I'm looking for. Let's plug in what we know into the equation. P is equal to 3.5 e to the 0.015 times 30. Lucky for us, variable is already by itself. I just got to type into my calculator. 3.5 e to the 0.015 times 30. Population should be 5.5 million. Don't forget to put that million after there. That's a very different number than just 5.5. Find the time that it would take for the population to be 7.3 million. Here's my variables again. So it wants to know what happens, or how long would it be for it to be 7.3 million. Still starts at 3.5 million, still grows by 0.015. This time we're just looking for time. So 7.3 equals 3.5 e to the 0.015 t. So just like before, we got to get that power by itself. So we'll divide both sides by 3.5. 7.3 divided by 3.5. Ooh, that's not a nice number. I might change that back to its fraction. 73 over 35 equals e to the 0.015 t. Power is alone. Time to change to exponential form. Log base e is ln of 73 over 25. We definitely didn't want to use that as a rounded number. It would give me a very different answer. 0.015t is my exponent. So ln of 75 over 25, or you could have used second answer there if you'd like. Now I have no option. And here's where I was talking about if it can be changed to a fraction, do it. But this one won't be able to be. 1.0986 equals 0.0515t. We'll divide both sides by 0.015. And I get that t is equal to 73 years.